Everybody, my name is Berry, and today we'll be proving that any function in two dimensions, well, a function that takes in two inputs like z of x comma y, cannot be both continuous and injective. So, first of all, let's define what injective means before we get to the board. For example, let's take y is equal to x squared. Y is equals to x squared is not an injective function. Why? Because if you want the output y is equal to 4, you can plug in x is equal to 2, or you can plug in x is equal to negative 2, and badum, you can get the same answer. But y equals x cubed is injective. Why? Because if you want 27, you can only plug in 3. Plugging in negative 3 gives you negative 27. There was only one input that gives you a specific number. So injective basically means every single output has less than or equal to one input corresponding to it. All right, so let's go over to the board to prove that any function of two variables is both continuous and injective. Specifically, any single variable function, if this is continuous and injective, that implies that it is monotonic. What does monotonic mean? Well, it means either f prime of x is always greater than 0, or
what is that you're trying to prove?
We're trying to prove that any function of two variables cannot be both continuous and injective.
And what grade level is it?
Definitely not in the high school. It's a little bit like first year, second year. Okay, either f prime of x is greater than 0, or greater than or equal to f prime of x is less than or equal to 0. So that's what we mean by monotonic. Now, in a simpler fashion, either our function is always increasing or our function is always decreasing. So for example, y equals x cubed is always increasing. That's why it's both continuous and injective. All right, so let's first formalize our definition of injective. A function f from domain R to codomain R is injective if and only if for all b inside the range of f, or for all b inside f's output, f of r. Actually, let's generalize this from a domain A to a domain B. Is injective if and only if for all b inside the codomain or our range, capital B, there exists less than or equal to 1 A inside A, such that f of A is equal to B. So that means everything in the codomain can either have one thing mapping to it or 0 things mapping to it. All right, great. So now that we've formalized our definition, let's start work towards our weaker one-dimensional version. That if a function in one dimension is continuous and injective, it has to be monotonic. So what I'm going to do is a little bit of an informal proof with a drawing. So in one dimension, what's going to happen? Well, I'm going to draw something that is continuous and supposedly injective, but not monotonic. Okay? So here's our graph, and over this interval, let's say it's monotonic. For any graph, you can find some small interval over which it's monotonic. But then let's say there's a bit of a divergence. Over here, f prime of x is always less than 0, but now let's say it changes its mind somehow and starts deciding to go upward. All right. So that itches. This looks a little bit unrealistic. I think I'm going to go for this instead. And of course, it can keep going upward, or it can change its mind again and start going downwards. Okay. So now, here's what we're looking at. As you can see, there's a relative minimum and a relative maximum in this graph. Technically, this whole interval is a relative minimum, and this is a relative maximum, or local maximum and a local minimum. Okay. So these are some pretty interesting points, right? But now, how are we going to prove that something is monotonic if it's continuous and injective using this format? Now, as you can see, this function is clearly not very injective. If I draw a line right over here, as you can see, it's going to intersect. Oh, no, I think we can just use white. It's going to intersect 2 points, which means that 2 different x values give you the same exact y value, which goes against our definition of being injective. So clearly from our drawing, this is not very injective. So what you might say is, well, why not just correct it to go downwards? But of course, that would make it a monotonic function. And still, we have this little point over here, which exhibits the same thing. So you might say, okay, well, why not make it just straight? Well, that poses the same exact issue. That will make it monotonic increasing because of this pesky little or equal to sign. So that's our informal proof. But of course, we need something a little bit more formal than just drawing a line. So what are we going to do? Well, let's do it on the maximum that we have over here instead. So let's say this maximum occurred at some point P, right? So now you'll notice that if I draw a line anywhere near the maximum, you'll notice that it cuts right through these 2 places. All right, but how do we officially, for real, prove that? Well, let's say we have P plus minus epsilon for some epsilon greater than or equal to or greater than 0, and we have P plus epsilon. And now let's call this maximum M, right? So that means that this is going to be M minus, who knows, delta. So now, here's the thing. As we decrease epsilon right over here, so this is what we're looking at right now, as we continue decreasing epsilon, these guys are going to get closer and closer and closer. But the main difference you'll see at a local maximum is that if x is less than p, f prime of x is going to be positive in this scenario. If x is greater than p, it's going to be negative. So what does that mean over here? That means that f of p minus epsilon for some range has to be less than f of p for epsilon less than a certain amount. In this case over here. Well, technically it has to go up a little bit further, but we could just say, for example, it somehow has a seizure and decides to skyrocket right over here, in which case this is our last possible point. So we know that epsilon is less than a certain amount. This is true. We also know when epsilon is less than a certain amount. This is true. For the exact same reason. All right. So we know that this is going to be, oh crap, I don't know how I did that, less than f of p. And we also know this is going to be less than f of p. Okay, we're making progress here. So that means that we don't know which one of these is greater, right? But let's just take the minimum of each of them. If f of p minus epsilon is less than f of p plus epsilon, just create a new variable, epsilon 1, that is greater than epsilon. No, less than epsilon. But let me think. Yeah, less than epsilon. So, for example, in this scenario, it's totally equal. But let's say we completely and irreparably change this graph. This is why I like smartboards. They don't leave a big smudge. Of course, I could use the professional chalk eraser, but that'll get everything everywhere. Okay. So in this case, as you can see, p plus epsilon is clearly a lot greater than p minus epsilon, right? So this is true. So now all we have to do is define a epsilon 1 that is less than epsilon. So this could be p minus epsilon 1. And now this is a lot closer, which means it has less of an opportunity to go down, which means it's naturally going to be closer to this value. And of course, I guess we can keep continuing until at some point it's less than this. It's greater than this. So we define epsilon 1 is less than epsilon. And of course, we can actually set epsilon 1 to some arbitrary limit, like epsilon over 2. So then, epsilon 2 can be epsilon 1 over 2, which can be epsilon over 4, and so on and so forth. Now, eventually, this is, of course, going to converge to f of p as epsilon approaches to 0. And by the laws of continuity, when x converges to p, then that means that f of x is going to converge to f of p, since we have a continuous function. So that means if we keep decreasing this, eventually, at some point by the Archimedean principle, this is going to have to be at a lesser distance or have a lesser difference from f of p than this guy right over here. Because this has to be some finite non-zero distance. So that means eventually at some point, if this is 0 and this is our distance, we can have this, have it again, have it a third time, have it a fourth time, and suddenly we have something that's less than this distance right over here. So formally, by the Archimedean principle, there exists some natural number k such that epsilon of k is, f of p minus epsilon k minus f of p Let me erase some things for a second. This difference is less than f of p plus epsilon minus f of p, and f of p minus epsilon k plus 1, oh sorry, this would be greater than, and this would be less than. Then, by the intermediate value theorem, did I really do that? Then by the intermediate value theorem, there exists some c between p minus epsilon k and p minus epsilon k plus 1, such that f of p minus, f of c is equal to minus f of p is equal to f of p minus f of p plus epsilon, which in other words means that this, I don't know why I'm adding unnecessary absolute value signs, which means that this is going to have to be the same value as this. But of course, this is between p minus epsilon k and p minus epsilon k plus 1, which is explicitly less than p, which is itself less than p plus epsilon, which means c can't be the same as p plus epsilon, which means that we've just found two x values that give the same y. Thus, this guy is not injective. So, we've found that any continuous and injective and non-monotonic function cannot exist. So if your function is continuous and injective, it has to be monotonic. All right. So now we can.
We're not done?
No.
How
so
long?
5 minutes.
Oh, really?
Now we can do a very elegant proof using this.
So what do we call the part 1?
This is proving that a one single variable function, if it's continuous and injective, it cannot be. It has to be monotonic.
And then what are we going to do now?
We're going to show that a function.
One second. I'm not.
Why are we ending?
We are studying the new one because lots of people not joining. This time, I believe lots of people are going to join.
But this is going to be 3 minutes at most.
Yeah, explain the second part.
Okay, so we have some function of two variables, and we're going to show that if it's continuous, it cannot be injective. Okay, I should add a red X instead of this. So, how can we show this? Well, let's say we have our surface over here, right? And it's totally continuous, so it can't be anything messy. So, take some green surface. Why do we have 3 different greens? Like, we're not going to be drawing a forest or anything, okay? Not the best surface drawer, but... So we have this 3-dimensional surface right here. And what I'm going to do is I'm going to take a little cross-section of it. So I'm going to take this as one cross-section. And the value of this guy, as you can see, we're keeping y constant and changing in the x. which means that this cross-section can be described by f1 of x is equal to z of keeping y constant at some value c1 and letting x change. Z of x comma c1. Meanwhile, we can take some different cross-section. So this is c2, this is c1. We can take some different cross-section. f2 of x is equal to z of x comma c2. When we're taking a partial derivative with respect to the x direction, we're actually just finding the slope of these guys over x. All right. So now we have these two cross sections, right? And they actually can't be like this, buddy-buddy. Because if f1 of x has some value, then f2 of anything cannot be equal to that value. They have to have two separate zones of operation. So one is going to go up and the other is going to go down. Pretty simple, right? And of course, well, now we kind of run into a very small problem, right? Because this one has to extend some way, but I guess we can just do this. So it's actually not much of a problem. Okay, so we have these two cross sections, right? Good. So nothing is taking up the same, there are no two z values that there is no z value that can be generated by two different points or more. So we're doing good so far. But now, let's say I have a third cross section somewhere in the middle, right? So this is going to, what are you doing? This is going to be at C2, and this is going to be at C1. So we're going to run a third one through the middle. Now, in order to not infringe on anyone's territory, it has to be constant, just a line with zero slope. Why? Because this is going to be the minimum of C2. Nobody can go above this line. This is going to be the maximum of F1. Nobody's going to go above this line. So it cannot increase because at some point it's going to hit the ceiling and then it's going to have to stagnate anyway. So it might look a little something like this. And now realize that that has to be the fate of literally every single cross section besides these two guys right over here. Oh, but actually it can't be. Why? Because F3 over here has now restricted the borders even more. So what is F4 going to do? I have a very orangish color. So F4 over here is now even more restricted. But that's not the biggest problem. The biggest problem is what happens when these two guys converge on each other. What happens if C1 approaches C2? So, in that case, what happens is that this guy gets squished between the two. And here's the problem with that. Because eventually, these two guys are going to be cross sections right next to one another. But here's the thing. They literally can't share a z value, which means that any line that we take approaching from this direction, it's going to see one z value here, but it can't see the same z value here. It's going to have a totally different z value, which means that we are going to have to deal with z of x, y as x approaches a and y approaches b not being equal to z of ab. Because in this case, x is approaching a, y is already at b, let's say. But then this, which is right next to our little function, does not have the exact z value of the function, of this function right over here. So in other words, this limit is not equal to this value because we're bringing together two cross sections that don't fit, which means that we're going to have an undefined, sorry, how can I put this? Yeah, we're going to have essentially a discontinuous function. Or you can do it the other way and show that it can't be injective. Because after this, what happens? Well, I guess it could be shown better like this because it can only go in one direction. And so that means that we're going to get another one which is going to stick in here, and another one that sticks in here, and another one that sticks in here. And eventually the cross sections are all going to approach a straight line, but then that tradition is going to be broken right here at C1 or at F1. And of course, if F1 is not a straight line, but everything around it is, that means there's going to be a discontinuity over here. So, I mean, I know this one is a little bit harder to visualize than our classical example over here, but imagine it like this very neat plane, except we have a little strip of paper, for some reason, diverging from everybody else. You see, that's not continuous, is it? So that's it.